don't go away. We have another paper from University of Minnesota. Lucky your team. I think they're doing great. I don't know if this is actually the record of having 2 papers from the same group at SIGCOMM or not, but congratulations. So next paper will be on unveiling the 5G mid-band landscape from network deployment to performance and application quality of experience. And Aman will be presenting that paper as well.
Okay, so hi again, I'm not going to introduce myself, but again, I'm going to say that Rostan is, due to logistics, is not going to be able to be here, so I'm going to present his work. So this work focuses on actually the 5G mid-band, and it's a collaboration with iMedia, as well as University of Para in Brazil. So as we know, we have 5G deployment in low band, mid band, and high band. The high band, they actually differs in terms of the bandwidth that's available in each one of them, as well as their sensitivity to obstruction. So if we take the millimeter wave, we can actually reach up to ultra high throughput. However, it's very sensitive to obstruction. Compared to the low band, where you actually have lower bandwidths and definitely higher coverage and less sensitivity. So if we actually compare currently the deployment, we'll find that only 7% of the global 5G deployment focuses on millimeter wave due to the issues that we have mentioned. You can also refer to the papers from our initial in 2020 from our group that talks actually more about the millimeter wave and its characteristics in dub and IMC. And there is minimum unused spectrum in terms of in terms of the low band 5G. So that's why 5G mid-band is the favored for deployment. And we have around 71% of the current deployment globally. However, low or minimal information is actually known about this mid-band. So for example, how about its deployment landscape and what are the different carrier configurations for this mid-band? And then what's the performance footprint? How it's compared to millimeter wave? Can it achieve this high throughput or not? And what's the implications of using 5G on the different application QoE? The third question we are interested in, some actually use mid-band or call mid-band as the sweet spot. So why this is the case? So we're interested to answer these questions. And in order to do that, we have actually conducted an extensive measurement in different cities in Europe and US using different operators in each one of them, as well as different smartphones. And as far as we know, this is the first cross-continental cross-operator in-depth measurements for 5G mid-band. These are some sample cities that we have actually conducted our measurements, as well as the operators that we have used in each one of them. So you'll see 2 or 3 operators in each. We have definitely purchase SIM cards in order to be able to work on these different operators without any limitation on the throughput that we can get. We deployed multiple servers and so on. For more information about the methodology, the data sets and tools, you can actually refer to our GitHub and our paper for more details. So first, let's try to understand the first question. What are the different deployment configuration for the different operators in Europe and US, and how they compare to each other? So if we start with Europe, we actually find that it has some sort of a uniform deployment. Their operators use the band N78, and they are using different channels ranging from 80, 90, and 100 megahertz. And they use the time duplex division mode. However, we can actually notice that some same operators are using different configurations. So for example, if we actually take Vodafone, in Italy, it uses 80 megahertz versus Spain, which uses 90 megahertz. And this definitely depends on the spectrum availability in each country and the regulations and so on. When we go to the landscape in US, we find that it's actually more diverse. So we have, for example, T-Mobile, which uses N41 TDD and uses N25 as an FDD, which is the frequency duplex division. And each one of them has the different bandwidths, and some of them have 40 and 100 megahertz versus 20 and 5 and so on. For Verizon and AT&T, they actually use the band N77 with 40 and 60 megahertz. And the reason is that more diverse is, again, due to the limited spectrum that's available to the different operators. The different carriers in US have actually deployed carrier aggregation in order to boost their performance, as we discussed in our other paper, which is SIGCOMM this year by way. So please refer to this paper if you're interested to learn more about the carrier aggregation in US. However, in Europe, they haven't deployed any carrier aggregation at all. So now we are interested in order to see what's the impact of this configuration on the physical layer performance. So we're going to first start with the physical downlink throughput, and then compare the different operators. For some reason, the operator names are not shown properly. So I apologize for that. You can actually refer to that from our paper. So for the different operators in Europe, again, they're using between 80 and 100 megahertz. And one thing to notice is that among them, the wider channel doesn't actually correspond to the higher throughput. So if we notice here, we'll find that Vodafone Italy has the best performance, while it actually has this 80 megahertz bandwidth channel. When we compare Vodafone Spain and Orange Spain, we will find that, again, the 90 megahertz actually outperforms the one which has the 100 megahertz channel. For the US operators, these are the throughput that they are getting without actually carrier aggregation. When you have carrier aggregation, this throughput goes beyond that. So if we actually want to dig deeper into the Spain case between Vodafone and Orange and try to understand why this performance is actually different. So now we are going to ask some questions in order to try to answer that. Could be, is it because of the number of resource blocks or elements that are allocated to one operator is actually larger than the other, and then hence lead to a higher throughput? And we find that the answer is actually no. Orange Spain, actually the one which has the higher bandwidth, gets the more resource blocks allocated to it, which is the green line, as you can see here. However, it doesn't correspond to the higher. So it's actually, Orange is going to be the 557.4 on average megabits per second, and the first one is going to be Vodafone Italy. Oh, Vodafone Spain, I'm sorry. So now we go to whether the QAM, the modulation, is actually the reason why behind this performance that we are seeing. And again, there are some differences. However, it's not sufficient to actually explain the different performance that we're actually seeing. So what about the MIMO layers? Could that contribute to the different performance that we're actually seeing? So if we actually measure that, again, I apologize for why I don't know this has happened, but anyway, so the 87.1% and the 83.8% actually shows the number 4 MIMO layers, which is the highest, and compared to 13.8 in case of the Orange 100 megahertz channel. So we actually see that the impact of the MIMO layer is the contribution or the main contributor for the performance that we're seeing. Now we're interested to ask why the number of MIMO layers actually reflect into that compared to the other factors. So when we compare actually the signal strength that we receive for Vodafone Spain and Orange Spain, we find that the one for Vodafone Spain is actually much higher. And the reason we attribute that to is the dense base station deployment for Vodafone, where you can actually see we have 3 base stations in just this zoomed location versus 2 in case of Orange. We have conducted more performance analysis in terms of the upper link physical throughput as well as the latency, but due to the time limitation, we're not going to go into them. So please refer to our paper for more details about these performances. So now we are interested into seeing how these different configurations for the midband impact the quality of experience for the different applications. So this is a video streaming example, and here we actually have 3 dots that are supposed to be close to these numbers. We have the normalized bit rate in here, and the stall time on the x-axis, and the better quality of experience is basically the right upper corner for that figure. We did these experiments for different operators, and then we are actually seeing that these 3 different channels, they have similar physical layer average throughput, which was translated to a nearly normalized bitrate matching for the average throughput. However, when we actually compare the stall time, we find that there is actually a wide variation in that. So now we are interested into understanding why this is the case. So we attribute that to the different variation of these multiple dynamic factors into the channel variability. So we came up with a metric that we introduced in order to characterize the dynamic of these different factors and how they change by using the scale variability metric, which actually just measures how fast each of these parameters are actually changing. So the lower this number, the better the channel is more stable, and the higher, the worse. Then we compared the performance of this application QoE to the variability. So we compared the MIMO variability as well as the MCS parameters for the modulation. And the better variability is towards, again, the upper right corner, which is the lower the variability for both of them, then the better performance that we're actually having. So again, each one of these is actually mapped to another dot, which I think was here, here, and then the other one was here. So we can actually utilize this variability in order to explain why we have these different stall times. So the lower variability leads to a lower stall time, and vice versa. Here we actually have a zoomed example of these different configurations, how they actually change, and their variability as well. I'm not going to go into that example because, again, it's not going to be well. But anyway, we here just go into the buffer size and how it changes and so on, and how this variability impacts the stall time or causes that stall time. So please refer to our paper for that. We also, in the paper, discuss how applications can actually cope up with this channel variability. For example, we can change the chunk size and so on for the different applications to cope up with these, as well as what are the different factors that actually impacts this variability in terms of location, number of users, and so on. So again, please refer to our paper for that. Finally, we are interested to answer the question why 5G is actually a sweet spot across the different deployments. So in this case, we're going to compare millimeter wave and 5G midband in terms of different mobility scenarios. In the first case, comparing the downlink throughput. So if we compare the walking for midband and millimeter wave, we can actually see that here on the right side, we're actually comparing the variability of MIMO and MCS and relating that to the throughput variability that we are seeing. So we can see that the midband walking actually has less variability in terms of the MCS and MIMO, and hence corresponds to a lower throughput variability. Compared to definitely the millimeter wave, which is the other one that's higher in terms of variability. And in terms of driving, if you actually compare the midband and millimeter wave, again, you will actually see that lower variability for midband compared to millimeter wave. Now we're going to see the impact on the different applications, QoE. So if we compare millimeter wave and midband in terms of walking, we can actually see that the better QoE, again, towards the top corner. So yes, millimeter wave, due to this higher throughput, can actually give us a higher bit rate. However, it suffers from larger stall time compared to the midband. And if we actually compare the driving scenarios for millimeter wave compared to walking, so again, the higher speed for the driving will lead to a worse throughput in terms of millimeter wave. So just to conclude, this is the first cross-continental, cross-operator in-depth measurements that actually reveals the landscape of the 5G midband. We have shown you some of why it's actually complex in order to identify its characteristics, as well as provide some insights for the operators, how they can configure their 5G midband. And finally, we also gave some pointers for application developers on how they can actually utilize midband and how to make their application 5G aware. So these are the pictures of the people who have contributed. There is a lot of people actually contribute to this work as well as the previous work, so it's proper to give credit to them. Again, all the information is going to be on our GitHub. Rostand is actually looking for, again, academic and industry opportunities. So if you are interested, please reach out to him. Also, if you are interested to collaborate with us, please reach out to Professor Zili Zhang, whether from industry or academia. Thank you.
Hi, this is Cheng Hao from CHK. Thank you for your talk. Regarding the channel variability, did you do a similar like measurements to compare the mid-band and low-band of 5G? Because in the slides, I only see you compare mid-band and high-frequency band, yeah, millimeter wave.
So low band is actually not really interesting. So we were interested in the millimeter wave and 5G mid-band because the millimeter wave provides us with this high bandwidth that everyone is looking for. However, it's not stable at all, as we actually saw. So that's why we're trying to find why 5G mid-band is actually the sweet spot compared to millimeter wave, why everyone may refer to just the mid-band instead of the high variability, sorry, the high throughput of millimeter wave, but due to its wild fluctuation, it's not actually useful in some sense.
Okay. So where the variability like being like slower in the low band compared with in the mid band? Is that a point?
Yeah. I think we would expect to be that. So when we compare the mid band, it definitely has better variability than the millimeter wave, and the low band, I think, expected to have lower, even lower variability.
Okay, thank you.
Hi, Dan Kilper, Trinity College Dublin. So I'm wondering about the densification issues here. So did you have a chance to explore, I mean, first off, in the throughput measurements, is there a certain densification where you don't get any additional benefit? Is there a sweet spot in terms of densification? And then in the millimeter wave case, do you expect that the millimeter wave would perform better, or is part of the problem there that you didn't have a high density of access points for the millimeter wave?
So the main issue for the millimeter wave is that it's high fluctuation as well as the dead zone. So basically, there are some areas where we don't get the 5G signal at all. It's also high sensitive to any obstruction. If there is a train, you actually lose the signal. If you just put your hand, you lose the signal. So these were some of the results that we actually shown in our 2020 papers. However, I believe what the carriers are trying to implement is the multi-band, where we actually utilize the millimeter wave, but also refer to the mid-band as a safe signal. So if you have video streaming, for example, let's try to do the base layer where we have the base frames using the mid-band. If we have higher bandwidths, then we can actually improve the quality instead of just like not doing anything. And with the carrier aggregation, I think also that helps a lot with the mid-band, as we have shown in our other paper. So this definitely boosts the throughput that we are using given the mid-band. So we can achieve, I think, even similar throughput based on this carrier aggregation to the millimeter wave.
Okay, but sorry, for the other case where you're just looking at the throughput, but at the mid-band only and comparing the two, so you saw that because I think it was orange, wasn't a high density deployment, but is there a sweet spot where if it's has a certain density, then you're always getting the maximum throughput and there's no point in making it denser, or did you find anything like that? Or?
I think definitely the more base stations, the better performance you're actually going to get. However, and this is one of the highlights that we actually wanted to highlight for the operators, is that they actually need to examine where they allocate their base stations instead of just doing it randomly. If they actually look into more of these results in depth, they can make some conscious decisions about where they are implementing their base stations. And we also believe that it's also expensive to implement these things, so it depends on their own strategy. But definitely the more base stations, the better performance we are going to get.
The question we haven't started, right? Because also we don't have the luxury to place the base station to study the optimal placement. I mean, just what the optimal density, because this is actually an interesting question, kind of interesting looking at.
But if you have different deployments, you can kind of walk around them and see, I don't know.
Right. So I mean, those are things are much harder to do without kind of collaborate with operators. So
Right.
start talking to some operators.
Yeah, it'd be very interesting. Thanks.
Great. Yeah, thank you so much. Let's thank Kamal once again for the great talks.